We're going to take our descriptions of rotational motion to now say, instead of just having something rotating about an axis, like a stationary bike like this, where we have something that's rolling like this, so we describe it with an omega, that is when this is going around, and then you can figure out the direction of the omega vector, compared to, and then we add that to basically translational motion. So we take this wheel and we just carry it along with some speed like this. So V, center of mass. If we can combine these two in just the right way, then we can describe rolling motion. And so what we know about rolling motion, right, for a bicycle wheel that's rolling, so this is going to be going like this, is that the wheel rolls, but the whole thing translates along. So this goes along like this. And so what we can do is we can describe, if we look at this, if the center of mass is going this direction, then, and this is just being carried, so this is just being slid or dragged, then the top of the bicycle wheel and the bottom of the bicycle wheel are going the same speeds. But we know that when something's rolling, at least for an instant, this is in contact with the ground, and if it's not slipping, that's actually a 0. And so what we need is we need to add this V to a V that's going like this. That's exactly the same speed, V associated with the rotation, so that this V plus this arrow give me a 0. So if this is the right V, so this is equal to V center of mass from down here, then all of these points are going to be, I'm just going to look at the top point, that would be V center of mass, and then I'd have points here. Then what happens is that at the top, this goes to 2V center of mass, and I have this is just V center of mass because there's no rotation. So what this says is when I have rotation without slipping, then the center of mass travels with V center of mass, and omega is equal to V center of mass over R. Okay, that's our usual kind of relationship. And that's what allows us to have V equals 0 right here at the bottom as the wheel comes in contact. If that's the case, then we'll also say that alpha is going to equal A center of mass over R, and we can just do all of the work that we've done before that was just for something rotating on its own. We can now look at rolling. And so I want to do a fairly simple idea here of an object rolling down an inclined plane. I know you're thinking, an inclined plane. Physicists love inclined planes. The reason we do these is because they give us a simple way to have gravitational potential energy. We can think about something rolling downhill. Okay, so here's my object. It's going to, let's say we start from rest, so we start from V equals 0, and we want to know our V final given a hill of height h. What does it depend on? And so I'm just going to do this from an energy point of view so you can see how all the pieces fit together. So energy initial at the top and energy final at the bottom. Right, so at the top I've got mgh, right? If I call this my y equals 0, and my u at the bottom is equal to 0. So U initial, and then kinetic energy initial is equal to 0, and down here the kinetic energy, I need to have kinetic energy of rotation, which is 1/2 I omega squared, and translation of it moving linearly downhill. So this is our normal 1/2 mv squared. And we have both things, because if it were just rotating in place, we'd have just this first one. If it were just sliding, we would have this. So what happens is the potential energy needs to go both into what we would get if we were sliding on a frictionless surface plus rotational energy. And so this gives us mgh is equal to 1/2 I omega squared plus 1/2 mv v squared, and in place of this omega, we can put our v, this is really v center of mass, right? Because that's the center of mass of the object, because all parts of it are moving at different speeds. V center of mass over the radius, and so this gives me mgh plus 1 is equal to 1/2 I over r squared v center of mass squared plus 1/2 m v center of mass squared. And then depending on what the object is, we can put in our moment of inertia there. If it's a disk, then we can put in a 1/2 mr squared. The m's will all cancel, the r's will go away, and we'll get the height. If it's a ball, a sphere, then we can put in an I of 2/5 mr squared. So we'll see how this works when we actually work problems. My point is that as you have something that's rolling, so rolling without slipping, then we have to include our kinetic energy of rotation as well as our kinetic energy associated with it just sliding down the incline.